Competition in quantum computing, Google Willow vs Microsoft Majorana 1. Date, February 25, 2025. Event summary. The race for supremacy in quantum computing has seen significant advancements, particularly with the emergence of Google's Willow and Microsoft's Majorana 1 systems. Both companies are at the forefront of quantum technology, looking to solve computational problems that are beyond the capabilities of classical computers. While they share the common goal of advancing quantum computing, their technological foundations, approaches to error correction, scalability, and potential applications differ markedly. Technology foundations. Google Willow. Google's Willow is built on the infrastructure of superconducting transmon qubits, which operate at temperatures close to absolute zero. This design enhances its capability to process quantum information through the use of superconducting circuits. Willow is an evolution of Google's previous Sycamore processor, which famously demonstrated quantum supremacy by completing a task in 5 minutes that would take classical supercomputers approximately 10 septillion years. Google aims to scale up its qubit count to 105 while enhancing its error correction capabilities. The cooling method employed by Willow is similar to that used in other superconducting systems, utilizing dilution refrigerators to achieve the necessary low temperatures for operation. Microsoft Majorana 1. In contrast, Microsoft's Majorana 1 leverages a fundamentally different approach by utilizing topological qubits derived from Majorana Zero Modes (MZMs). These qubits are designed to be inherently stable, which reduces the reliance on software-based error correction. The compact architecture of Majorana 1 allows it to fit into a palm-sized package, offering a practical edge in terms of deployment. Unlike Google's multiple physical qubits for each logical qubit, Majorana's architecture allows for 8 physical qubits to combine into a single logical qubit, which is a significant distinction in their respective designs. Qubit count and stability. Google's strategy hinges on increasing the number of qubits to enhance error correction efficacy. The design philosophy posits that more physical qubits translate to better performance in error correction, albeit at the cost of needing a larger number of qubits overall. Conversely, Microsoft's focus is on achieving greater stability with fewer physical qubits, suggesting a streamlined approach in the quest for effective quantum computations. Error correction strategies. Google Willow. Willow's approach to error correction revolves around the concept of scaling up qubits. Google has demonstrated that increasing the physical qubit count contributes significantly to the performance of logical qubits. This strategy not only improves error correction but also paves the way for more complex quantum computations. Microsoft Majorana 1. Microsoft's Majorana 1 capitalizes on the natural error resistance of topological qubits. The inherent stability of these qubits reduces the necessity for extensive software-based error correction. Recent advancements in measurement techniques have enabled precise control over electron interactions, exemplified by the detection of a single electron difference in a billion-electron system. This level of precision underscores the potential of Majorana 1 in performing reliable quantum computations. Scalability and commercialization. Google is taking a more gradual approach to scalability, with plans to exceed 10,000 qubits by the early 2030s. Initial applications are aimed at drug discovery and advanced nuclear fusion simulations. This methodical scaling reflects a focus on refining existing technology and enhancing error correction capabilities. Microsoft, on the other hand, has set an ambitious target of achieving 1 million qubits by 2027 to 2029. The applications envisioned for Majorana 1 include innovative solutions for microplastic degradation and self-healing materials. However, experts express skepticism regarding Microsoft's timeline, noting previous delays in the development of Majorana qubits. Industry impact and future outlook. Both Google's Willow and Microsoft's Majorana 1 have the potential to disrupt various industries, particularly in cybersecurity and materials science. Quantum computing capabilities could eventually challenge existing encryption methods, necessitating the development of post-quantum cryptography solutions. In materials science, Microsoft's topological qubits could significantly enhance models of chemical reactions, while Google's superconducting qubits could optimize energy solutions such as battery chemistry and nuclear fusion. As both companies strive to integrate their quantum computing technologies into cloud services, Google Cloud and Azure Quantum, the future of quantum computing may require a synthesis of both approaches. Google's focus on refining existing technologies could complement Microsoft's innovative strategies for simplifying error correction. Conclusion: the competition between Google's Willow and Microsoft's Majorana 1 epitomizes the diverse paths being explored in the field of quantum computing. Each system has its unique strengths and challenges, contributing to the broader evolution of the industry. As the race continues, advancements from both companies will likely drive the development of practical quantum computing solutions, ultimately shaping the future landscape of technology. This report synthesizes insights from multiple sources regarding the competition between Google and Microsoft in the quantum computing arena, emphasizing the contrasting methodologies and potential future impacts of their respective technologies. The competition between Google's Willow and Microsoft's Majorana 1 in the quantum computing arena reveals several counterintuitive insights that challenge conventional wisdom regarding the scalability and error correction capabilities of qubits. Counterintuitive insights. 1. Qubit count versus stability. Traditionally, many in the quantum computing community believed that a higher number of qubits directly correlated with better performance and error correction. Google's Willow follows this paradigm, aggressively scaling to 105 qubits to enhance error correction. However, Microsoft's Majorana 1 adopts a counterintuitive strategy by emphasizing stability and efficiency with fewer physical qubits. This approach suggests that quality may trump quantity, challenging the assumption that more qubits always lead to better outcomes. 2. Error correction mechanisms. Google's reliance on increasing qubit counts for error correction may seem practical at first glance, however. It contrasts sharply with Microsoft's use of topological qubits that inherently resist errors. The notion that a physical qubit can be designed to minimize errors rather than rely on extensive software-based error correction strategies is a significant departure from traditional methods. This indicates that innovative qubit design may be more effective than merely adding more components to a system. 3. Commercialization timelines. Microsoft aims for an ambitious target of 1 million qubits by 2027 to 2029, which raises skepticism among experts given past setbacks in Majorana qubit development. Conversely, Google's more gradual approach of aiming for 10,000 qubits by the early 2030s appears conservative but may be more realistic. The counterintuitive takeaway here is that a measured incremental approach may yield more consistent advancements than aggressive large-scale goals, which can lead to overpromising and under-delivering. 4. Potential applications. While Google focuses on applications like drug discovery and nuclear fusion simulations, Microsoft's ambitions include addressing microplastic degradation and developing self-healing materials. The surprising aspect is that both companies are targeting vastly different applications, which suggests that the path to practical quantum computing may not be linear or uniform. Instead, different technologies may find their niches in unexpected fields, reshaping the landscape of quantum applications. 5. Cloud computing strategy. Both companies plan to offer their quantum computing capabilities as cloud services with Google Cloud and Azure Quantum. The counterintuitive notion here is that despite the intense competition, the commercial success of quantum computing may hinge on collaboration and cloud integration rather than pure competition. This reflects a broader trend in technology where platforms become more valuable through shared access rather than exclusive ownership. Conclusion. The competition between Google's Willow and Microsoft's Majorana 1 illustrates a landscape where conventional beliefs about qubit count error correction commercialization and application may not hold true. The differences in their strategies highlight the potential for diverse pathways to achieving practical quantum computing, suggesting that a synthesis of both approaches could ultimately be necessary to unlock the full potential of this transformative technology. In the ongoing quantum computing race, the competition between Google's Willow and Microsoft's Majorana 1 is marked by significant technological differences that may be easy to overlook but are crucial for understanding the future landscape of quantum computing. Below are key insights from the report that highlight these differences and their implications. 1. Technological foundations and qubit types. While many discussions focus on the number of qubits, the underlying technology and type of qubits used are equally, if not more, significant. Google Willow utilizes superconducting transmon qubits, which require extremely low temperatures and are built upon the existing Sycamore processor architecture. This foundation is important because it leverages well-understood physics, but it also means that scaling up to the desired qubit counts may face challenges related to error rates and thermal management. In contrast, Microsoft's Majorana 1 is based on topological qubits, which are theorized to offer intrinsic error resistance due to their unique properties as Majorana Zero Modes. This difference suggests that while Google may achieve a higher qubit count, Microsoft could potentially achieve greater stability and error correction with fewer qubits. This could lead to a scenario where Microsoft's approach could lead to more efficient quantum computations, as it minimizes the need for extensive error correction mechanisms reliant on software. 2. Error correction strategies. The approach to error correction reveals a fundamental difference in philosophy between the two companies. Google's strategy focuses on scaling up the number of qubits to enhance error correction, which inherently requires a complex interplay of many physical qubits to create a single logical qubit. This approach highlights a reliance on hardware scaling and extensive error correction protocols, which could become cumbersome as the system grows. Conversely, Microsoft's architecture aims to build error-resistant qubits at the hardware level. The topological nature of Majorana qubits allows them to potentially avoid certain types of errors altogether. Researchers have pointed out that this could lead to a more straightforward error correction process, potentially enabling faster and more reliable quantum computations. The significance here lies in the potential for Microsoft's approach to simplify scaling, as less overhead may be needed for error correction. 3. Scalability and commercialization goals. The ambitious scalability targets set by both companies reveal contrasting approaches to commercialization. Google aims for over 10,000 qubits by the early 2030s, with a clear roadmap towards practical applications in drug discovery and nuclear fusion simulations. This gradual scaling approach allows for iterative improvements and a more manageable path to commercialization. Microsoft, however, targets an aggressive goal of 1 million qubits by 2027 to 2029. While such ambitions are commendable, skepticism surrounds this timeline given historical delays and challenges associated with Majorana qubit development. This discrepancy in scalability goals raises questions about the feasibility of such rapid advancements and the potential risks involved. If Microsoft's timeline proves overly optimistic, it could hinder their position in the market and affect investor confidence. 4. Industry impact and future applications. An often overlooked aspect of the competition is the broader implications for various industries. Both systems are poised to disrupt fields like cybersecurity and materials science, but the nature of their applications may differ significantly based on their technological foundations. For instance, Google's advancements in optimizing chemical processes may lead to breakthroughs in energy solutions, whereas Microsoft's focus on modeling chemical reactions could lead to innovations in self-healing materials. The potential for both systems to impact cybersecurity is particularly noteworthy, as quantum computing could fundamentally change encryption methods. As both companies work toward achieving quantum advantage, the race to develop post-quantum cryptography becomes imperative. This aspect underscores the urgency for researchers and industries to prepare for a paradigm shift, as existing security measures may become obsolete. 5. Expert opinions and skepticism. Expert opinions on both technologies reveal a nuanced understanding of their strengths and weaknesses. While Microsoft's topological approach is celebrated for its theoretical advantages, researchers caution that fault tolerance and practical implementation remain unproven. On the other hand, Google's progress in error correction is more established, yet concerns about the overhead of scaling remain. These expert insights are significant because they highlight the ongoing uncertainty in the quantum computing field. Investors, researchers, and policymakers should be aware that while both companies are making strides, the path to practical quantum computing is fraught with challenges that could shift the competitive landscape unexpectedly. Conclusion. The competition between Google's Willow and Microsoft's Majorana 1 is not merely a race to achieve a higher qubit count, it represents two fundamentally different approaches to solving the challenges of quantum computing. The implications of their respective technological foundations, error correction strategies, scalability ambitions, and potential industry impacts are profound. As the race continues, the need for a synthesis of both approaches may become evident, particularly as both companies aim to offer their capabilities as cloud services through Google Cloud and Azure Quantum. Understanding these nuances is crucial for stakeholders in the quantum computing ecosystem, as they will shape the future of technology and its applications across various domains. 1. Technological foundations in qubit design. Google's Willow employs superconducting transmon qubits which operate at near absolute zero temperatures, focusing on increasing qubit count to enhance error correction. In contrast, Microsoft's Majorana 1 utilizes topological qubits based on Majorana Zero Modes MZMs designed to inherently minimize errors, which allows for potentially fewer qubits to achieve stable performance. This fundamental difference in qubit design reflects each company's strategic approach to overcoming the challenges of quantum computing, emphasizing the importance of hardware architecture in achieving scalability and performance. 2. Error correction strategies. The strategies for error correction between the two technologies are fundamentally different. Google Willow relies on scaling up the number of physical qubits to enhance error correction capabilities, evidenced by its ability to tackle complex tasks much faster than classical supercomputers. Conversely, Microsoft Majorana 1 leverages the natural error resistance of topological qubits, which minimizes the need for extensive software-based error correction. This distinction is critical as it affects not only operational efficiency but also the potential for practical applications in real-world scenarios. 3. Scalability and commercial ambitions. Both companies have ambitious goals for scalability, but they differ significantly in their timelines and approaches. Google aims to gradually increase its qubit count to over 10,000 by the early 2030s, focusing on applications in drug discovery and nuclear fusion. Microsoft, however, targets a more aggressive plan of reaching 1 million qubits by 2027 to 2029, with applications extending to innovative fields such as microplastic degradation and self-healing materials. This divergence highlights the varying levels of confidence and risk tolerance in their respective strategies, as well as the potential for market disruption based on their success or failure. For industry impact and future outlook, both quantum computing systems have significant implications for various industries, particularly in cybersecurity and materials science. They could disrupt existing encryption methods, necessitating the development of post-quantum cryptography. Moreover, both technologies have the potential to transform fields such as chemical modeling and energy optimization. The future of quantum computing may lie in a combination of both Google and Microsoft's methodologies, as each offers unique strengths that could complement one another in overcoming the challenges of achieving practical quantum computing solutions. The ongoing competition and collaboration in this space will be pivotal in shaping the trajectory of future technological advancements. 1. The Cold War space race, the competition between the United States and the Soviet Union during the Cold War to achieve significant milestones in space exploration. This rivalry saw the launch of Sputnik by the USSR in 1957, followed by the US landing on the Moon in 1969. Showcasing different technological approaches and ideologies. 2. The VHS versus Betamax format war. In the late 1970s and early 1980s, Sony's Betamax and JVC's VHS competed for dominance in the home video recording market. Despite Betamax's superior video quality, VHS won due to its longer recording time and broader licensing strategy, illustrating how market dynamics can influence technological adoption. 3. The browser wars. In the 1990s, the competition between Netscape Navigator and Internet Explorer defined the early web experience. Netscape's early lead was challenged by Microsoft's aggressive bundling of Internet Explorer with Windows, resulting in a rapid shift in market share and the eventual decline of Netscape, highlighting the impact of strategic business decisions in technology competition. The future of quantum computing is poised for significant advancements, particularly with the ongoing competition between Google's Willow and Microsoft's Majorana 1. Both technologies have unique strengths and weaknesses, and their evolution will likely shape the landscape of quantum computing in the coming years. 1. Technological advancements. Google Willow is focusing on increasing the number of superconducting transmon qubits, aiming for over 10,000 qubits by the early 2030s. This approach is built on enhancing error correction capabilities, enabling the system to tackle complex computations previously unmanageable by classical computers. As they refine their technology, we can expect Google to leverage its extensive resources and expertise in software and cloud computing to optimize the performance of quantum algorithms. Microsoft Majorana 1, based on topological qubits, aims for an ambitious target of 1 million qubits by 2027 to 2029. This innovative architecture minimizes errors inherently, potentially allowing for a more straightforward error correction process. If Microsoft can overcome the existing challenges in scaling its technology, Majorana 1 could offer unprecedented stability and efficiency in quantum computing applications. 2. Error correction evolution. Error correction is a critical barrier in quantum computing. Google's strategy involves scaling up the number of qubits to improve error correction. In contrast, Microsoft's approach relies on the natural error resistance of topological qubits. The future will likely see advancements in hybrid error correction techniques that integrate both companies' methodologies, enhancing the reliability of quantum systems. 3. Scalability and commercialization. The race for scalability will be a determining factor in the success of both technologies. Google's gradual approach may lead to steady improvements in real-world applications such as drug discovery and nuclear fusion simulations. However, Microsoft's aggressive timeline raises questions about the feasibility of achieving 1 million qubits in such a short period, as both companies continue to develop their technologies. The commercialization of quantum computing will accelerate. We can anticipate increased availability of quantum computing as a cloud service, allowing businesses and researchers to access these powerful tools without needing to invest in extensive hardware setups. 4. Application expansion. The potential applications for quantum computing are vast and varied. Google's focus on drug discovery could revolutionize pharmaceutical research, enabling faster and more accurate simulations of molecular interactions. Meanwhile, Microsoft's ambitions in materials science, such as self-healing materials and microplastic degradation, could lead to significant advancements in sustainability and environmental conservation. Moreover, both companies will likely make strides in cybersecurity. As quantum computers become more powerful, they will pose challenges to current encryption methods, necessitating the development of post-quantum cryptography. The race to secure data against quantum threats will drive innovations in both hardware and software security solutions. 5. Collaboration and synthesis. As the competition unfolds, It's essential to consider the possibility of collaboration or synthesis between the two approaches. The future of quantum computing may not be defined by a single victor but rather by a combination of methodologies that leverage the strengths of both Google's and Microsoft's technologies. Such collaboration could catalyze breakthroughs that neither company could achieve independently. 6. Regulatory and ethical considerations. As quantum technology matures, regulatory frameworks will need to evolve to address the ethical implications and security concerns associated with these powerful tools. Policymakers will face the challenge of balancing innovation with the need for robust safeguards against misuse, particularly in fields such as surveillance, data privacy, and cybersecurity. Conclusion. The future outlook for quantum computing, particularly regarding Google's Willow and Microsoft's Majorana 1, is marked by both promise and uncertainty. As both companies continue to innovate and refine their technologies, we can expect significant advancements in error correction, scalability, and application potential. The convergence of these approaches alongside the necessity for ethical considerations and regulatory frameworks will shape the next era of quantum computing, ultimately revolutionizing industries and unlocking new possibilities for scientific discovery and technological advancement.